Picture a puff of gas, a little cloud of atoms, the sort of thing you'd think is as boring as physics gets. Now start taking heat out of it. Not fridge cold, not liquid nitrogen cold, not the cold of deep space between the stars, colder than that. Colder than anywhere the universe has ever managed on its own. Keep going until the atoms have nearly stopped moving. And then something happens that no gas has any right to do. They stop being a swarm of separate little things and merge. Not chemically, not gluing together, but quantum mechanically, into a single wave, wide enough that you could photograph it. Matter, thousands of pieces of it, suddenly marching in step like one thing. And then the twist that turned this into a whole frontier. You pour that strange, obedient quantum stuff into a crystal made of nothing but laser light and use it as a stand-in for the guts of a solid you could never otherwise understand.
And I still get a thrill saying it, because every piece is literally true, not a figure of speech. The cloud really is colder than anything in nature. The atoms really do lock into one shared wave. People really do use it as a working model of a material. It's one of those corners of physics where the honest description sounds made up, and the fun tonight is that you already have, in your own coursework, almost everything you need to see why it has to be true.
Okay, I'm hooked, but I want to push back immediately because when you said single wave, my undergraduate reflex kicked in. Can we start from something I've actually done? Because it smells to me like this whole thing might just be two ideas I already own, sitting next to each other.
That is exactly the right reflex, and I'm delighted you have it. Tell me what two ideas. Wait, this is just the ideal gas and de Broglie, right?
Here's my suspicion. Idea 1. The ideal gas. In stat mech, temperature is basically just motion. A hot gas is atoms flying around fast. A cold gas is atoms moving slow. Heat is jiggle. Hotter means faster. Colder means slower.
Perfect. Hold that one.
Idea 2. De Broglie. In my first quantum course, the very first strange thing they teach you is that every particle is secretly also a wave, with a wavelength that goes as 1 over the momentum. So a fast thing has a tiny wavelength, a slow thing a longer one. Slower means a longer wave. So my question is this episode just those two holding hands? Cool the gas, the atoms slow down, their de Broglie waves get longer, and at some point something gives.
You've just laid down 2 of the 3 legs of the whole thing in 30 seconds. And your hunch that it's just those ideas holding hands is almost right. The best kind of almost, because the gap between almost and right is exactly one more idea you also already own, and it's the one that makes the magic.
There's a third leg. Of course there's a third leg.
And it's the strangest bookkeeping in quantum mechanics. You've met it, even if it didn't feel like a big deal. Identical particles. Take 2 atoms of the same kind, truly identical, and quantum mechanics says you're not allowed to label them. There's no little number 1 painted on one and number 2 on the other. Swap them and nothing physical has changed, and the theory takes that dead seriously.
Right, and there are 2 flavors, fermions and bosons. Fermions are the antisocial ones. Pauli exclusion, no 2 electrons in the same state, which is why atoms have shells and chemistry exists at all. And bosons are the other kind.
The other kind, and here's the sentence to keep for tonight, bosons aren't just allowed to share a state, they love to. The exact opposite of Pauli. Fermions elbow each other apart, bosons pile on. Give them the chance to be in the same quantum state, and they'll take it eagerly. And a great many atoms behave as bosons. So there's your third leg, cold gas, growing de Broglie waves, and particles that want to crowd into the same state. Now watch what falls out when all 3 meet, because this is the one idea I want to work out loud with you, slowly. It's worth the time. How a few thousand atoms become one wave. 4 steps. That's all it takes, and you've done 3 of them on a homework set. Step 1, and this one is not even quantum yet. Temperature is motion. Warm gas, the atoms are tearing around fast in every direction, random as anything. Take heat out, and they slow down. That's just your ideal gas. Nothing weird has happened.
With you, cold equals slow. That's the least controversial sentence in physics.
Step 2, and now the quantum leg comes in. Every one of those atoms is also a little wave, a fuzzy wave packet, a smear of where it might be. And by de Broglie, as the atom slows down, that smear gets wider. A slow atom is a fatter, more spread-out wave than a fast one. There's even a proper name for the size of that smear in a gas at a given temperature, the thermal wavelength, and the only thing you need to know about it is which way it moves. As the gas gets colder, that wavelength grows. Colder gas, fatter waves.
Okay, so let me hold the picture. At room temperature, my gas is a bunch of atoms, and each one is a wave, but a ridiculously tiny wave, way smaller than the space between the atoms.
Fantastically tiny. And that gap in scales is the whole reason gases look boring and classical in the first place. At everyday temperatures, each atom's wave is so much smaller than the distance to its neighbors that the waves never notice each other. Each atom is a little private ripple with a huge empty moat around it. They might as well be billiard balls. The wave nature is real, it's just hopelessly outmatched by the spacing.
So the game is to close that gap. Cool it down, the waves get fatter, the spacing stays roughly the same, and at some point the fat waves are as wide as the gaps between atoms.
You just said the entire punchline out loud. That's step 3, and it is the moment everything changes. Keep cooling. Each atom's wave swells and swells until it's about as wide as the distance to the next atom over. And now the waves aren't separate anymore, they overlap. They bleed into each other. And once they do, here's the thing that breaks your classical intuition. You literally cannot say which atom is which. Not it's hard to tell, you cannot even in principle. The wave of this one and the wave of that one are sitting in the same patch of space, and the indistinguishability we talked about stops being a philosophical footnote and starts running the physics.
And this is where the bosons cash in, because if they can't be told apart, and bosons love to share the same state,
then the moment the waves overlap, there's a stampede. It's a runaway. A few atoms drop into the single lowest energy state, and because bosons prefer company, that makes it even more attractive for the next atom to join them, which makes it more attractive still, an avalanche. Below a certain critical temperature, a huge fraction of all the atoms crash down into the very same quantum state. That's step 4. And now they are not thousands of separate little waves anymore. They are one wave, a single quantum wave function, one mathematical object describing the whole cloud at once. Quantum mechanics, the stuff we're always told only shows up for one tiny particle at a time, has been blown up to something the size of a speck you could see. That is a Bose-Einstein condensate.
I want to sit on that for a second because it's genuinely beautiful. And then I want to be annoying about the analogy, because you trained me to be.
Please be annoying, that's the job.
You keep saying the waves merge into one. My brain wants to turn that into the atoms squish together, fuse into a blob, physically stick to each other like a drop of glue. Is that what's happening? Are they clumping up?
No, and thank you, because that's the single most important place this picture can mislead you. Nothing is pulling them together. No attractive force, no glue, no clumping. The gas stays dilute. The atoms are still, on average, spread out with room to spare. What merges isn't their matter, it's their state. They come to share the same wave function, and the coherence of that state, the length over which it all marches in step, grows to span the whole cloud. So don't let merge into one wave harden into, they melt into a droplet. It's not togetherness of stuff, it's sameness of state, and what drives it is pure boson bookkeeping, the love of sharing a state, not any force. That distinction is the whole physics.
Sameness of state, not togetherness of stuff. Okay, that's a sharper sentence and I'll keep it. Now I have to ask the obvious one. How cold is cold enough? Because you keep gesturing at very cold, and I want the actual scale.
Right, and here's where I have to be careful, because there's a phrase people throw around that's just wrong. This happens a hair above absolute zero. Not at everyday cold, we're talking less than a millionth of a degree above the absolute bottom of the temperature scale. Colder, as I said at the start, than anywhere in the natural universe. The coldest deep space gets, the leftover glow of the Big Bang, is a few degrees above absolute zero. This is 1,000,000 times colder than that, and then some.
A millionth of a degree above absolute zero. So, basically at absolute zero, you've stopped the atoms. They're frozen still.
Ah, no, and I'm glad you said it that way, because that's the trap. You have not reached absolute zero, and the atoms are not frozen still, and both are deep facts, not nitpicks. Absolute zero is the idea of perfect stillness, zero motion, zero jiggle, and quantum mechanics flatly forbids that. Heisenberg won't let a particle have a perfectly definite position and perfectly zero momentum at once, so there's always an irreducible last shiver of motion left over, zero-point motion that you can never remove, no matter how hard you cool. And on top of that, the third law of thermodynamics says you can approach absolute zero but never actually reach it. Each remaining scrap of heat costs more and more to remove, without end.
So above absolute zero is doing real work in that sentence. The above is not a rounding error.
The above is load-bearing. 1,000,000th of a degree above absolute zero is honest and staggeringly cold. At absolute zero is a small lie about how the universe works. The atoms are unimaginably cold and slow, but not switched off. That quantum shiver stays forever.
I love that the honest version is barely less impressive than the fake one. And I have to ask about the title, because you called this 1,000,000 atoms, one wave. And I've been quietly counting. Is it exactly 1,000,000 atoms?
Caught me. No. 1,000,000. There is a poet's number, not a census. Real condensates run from a few thousand atoms in the small early ones up to many millions in the big machines. I say 1,000,000 because it paints the right picture. Something macroscopic, something you could see. But if you walk away thinking a condensate is precisely 1,000,000 atoms, I've misled you. The count doesn't matter. However many there are, thousands or millions, they're described by one wave function. One wave. That's the miracle at any number.
One wave, whatever the count. Got it. So this is gorgeous in principle, but somebody had to actually make it. How on earth do you cool a gas to 1,000,000th of a degree above the bottom of everything? I can't even picture the fridge.
There is no fridge. There couldn't be. Any wall you put near this gas would be blisteringly hot by comparison and wreck it instantly. The cooling is done with light, and then with a trick so simple it's almost funny. It's a genuine triumph of cleverness, so let me walk it. 2 ways to steal heat. It comes in 2 stages, and you need both. That's important, so flag it. Stage 1 is laser cooling, and the idea behind it is lovely once it clicks. You'd think shining lasers on something would heat it up, right? Lasers are how we cut steel.
Yeah, cool it with lasers sounds backwards. Light carries energy in. That should make things hotter.
It sounds completely backwards, and the fix is beautiful. A photon doesn't just carry energy, it carries a tiny kick of momentum. Absorb one, and the atom gets shoved a little in the direction the light was going. Now set up 6 laser beams, one from each direction, tuned just below the frequency the atom likes to absorb. Here's the trick. By the Doppler shift, an atom moving toward a beam sees its color shifted up, closer to what it absorbs. So it preferentially drinks the photons coming at its face, the ones pushing against its motion.
Oh, so whichever way it tries to move, it runs into more of the light, shoving it backward. Like a headwind, no matter which way you run.
Exactly like a headwind, from every direction at once. Physicists call it optical molasses, a thick, viscous drag, whichever way the atom goes, so it slows. Add a bit of magnetic trickery to hold the cloud in place, and you chill the gas into the range of millionths of a degree, the micro-Kelvin range. And that trick, cooling and trapping atoms with light, won its own Nobel Prize in Physics in 1997 to Stephen Chu, Claude Cohen-Tanuji, and William Phillips.
So we're already at a millionth of a degree from the lasers alone. Aren't we basically there?
You'd think. But no, and this is the honest catch. Laser cooling hits a flaw. There's a limit to how cold the light and momentum game can take you, and it stops short, well short, of where the condensate forms. Laser cooling alone cannot make a Bose-Einstein condensate. Full stop. You need a second stage, and it's the funny simple one.
Okay, hit me.
Evaporative cooling. Exactly what it sounds like, and it's how your coffee cools down. The fastest, hottest molecules at the surface escape as steam, and when the hottest ones leave, the average energy of what's left drops. The coffee cools because its most energetic molecules run away.
So you do that on purpose, to the atoms?
On purpose and with exquisite control. Your laser-cooled cloud sits in a trap. Think of it as a bowl. Now slowly lower the rim. The hottest atoms, the ones with enough energy to climb the walls, escape over the edge and are gone. What's left reshares its energy and settles colder. Lower the rim again, spill the next hottest, and so on. You skim the hot atoms off the top, over and over, and the survivors get colder and colder.
But you're throwing atoms away. You must end up with far fewer than you started.
You pay dearly. You might throw away the vast majority to get the rest cold enough. That's the tax. But it works. This stage carries the gas from millionths of a degree down to billionths, the nano-Kelvin range, across the line where the condensate forms. Laser cooling to reach the ballpark, evaporation over the finish line. Both stages, every time, and that's most of why this took as long as it did.
How long did it take? You said Einstein's name is on this thing, and Einstein is, a while ago. June 1995.
A wonderful gap, and the idea itself is old. Building on Satyendra Nath Bose's statistics for light quanta, Einstein extended it to atoms of matter in 1924 and 1925 and predicted exactly this. Cool bosons below a critical temperature, and they pile into one lowest state. Then it sat untouched for about 70 years. The required cold seemed absurd. The first true condensate finally came on the 5th of June, 1995, at a lab called Giller in Boulder, Colorado, a joint institute of the U.S. National Standards Lab and the University of Colorado. Eric Cornell and Carl Wyman took about 100,000 rubidium atoms, the kind called rubidium-87, in a magnetic trap and ran exactly the two-stage cooling we just described. And as the gas crossed the threshold, around 170 billionths of a degree above absolute zero, a sharp spike appeared in the middle of the cloud, a dense core of atoms all in the same state, the condensate.
170 billionths of a degree, and you can actually see the moment it happens.
You can, and it's one of my favorite images in physics. Let the trap go, let the cloud expand a moment, and take a shadow picture with a flash of light, and you get a map of how fast the atoms were moving. A normal warm gas is a broad, round, featureless smudge, atoms flying every which way at all speeds. But as they crossed into the condensate, a sharp, tall peak stabbed up out of the middle of that smudge. A huge population of atoms, all barely moving, all in the same lowest state. You are, as directly as it gets, looking at a photograph of the wave function. They cooled further still to around 20 billionths of a degree and got an almost pure condensate. The whole cloud in one state. Read that slowly, 2/100ths of a millionth of a degree above absolute zero.
2/100ths of a millionth of a degree, that's where I stop being able to feel it.
Nobody can feel it. And a few months later that same year, Wolfgang Ketteler at MIT made his own condensate out of sodium atoms, with far more of them, and because he had so many, he could do something spectacular. Split a condensate in two, let the halves overlap, and watch them interfere. Stripes. The same crest meets trough, crest meets crest fringes you saw in the double slit, but made of matter on a scale you could photograph. About as direct as proof gets that these are real coherent waves. And in 2001, the Nobel Prize in Physics went to Cornell, Ketteler and Wyman for making Bose-Einstein condensation real and for the first studies of these strange new drops of matter.
So that's the thing itself. Proved, done, real, medals handed out. A new state of matter made to order. Where does the frontier part come in? Because we made a weird cold cloud is amazing, but you promised me a stand-in for the insides of a solid.
That's the turn, and it's where this stops being a beautiful curiosity and becomes a tool. And it starts, of all places, with a complaint Richard Feynman made in 1982. An egg carton made of light. Feynman was chewing on a hard truth. Try to simulate a quantum system with many parts, say all the electrons in a chunk of material, pushing and pulling on each other, on an ordinary computer, and you hit a wall almost at once. The memory you need to track it honestly grows explosively with the number of particles. Add a few more, and you blow past every computer that could ever be built. It's not that our computers are too slow. The problem is exponentially hard for a classical machine. Feynman's fix was radical and simple. If a classical computer can't do it, don't use one. Build another quantum system you can control and measure, set it to obey the same equations as the thing you care about, and let it run. Use one piece of quantum nature to imitate another.
So instead of computing the answer, you build a physical thing that has to obey the same rules and read the answer off the thing.
You let nature do the computation. And a Bose-Einstein condensate is stunningly good raw material for it. Clean, cold, quantum, full of knobs. Here's the move. Shine a couple of laser beams back against each other so they form a standing wave. Bright and dark stripes that just sit there in space. Do it in 2 or 3 directions and you get a 3-dimensional grid of spots, and the atoms get nudged to sit in it, one pocket, the next, a regular, repeating array.
An egg carton. You've built an egg carton out of light and dropped one atom into each dimple.
An egg carton made of light. That's exactly the picture, and let me tell you where it beats a real egg carton, because that's the point. A real crystal has atoms in a repeating grid too, with electrons hopping around, but it's a mess. Defects, missing atoms, impurities, constantly vibrating with heat. Your egg carton of light has none of that. It's perfectly regular, defect-free. It doesn't vibrate the way a warm solid does, and, here's the magic, you change it at the twist of a knob. More laser power, deeper dimples. Less, shallower. A crystal whose properties you dial in real time. A solid without the mess. And that artificial cleanliness isn't a flaw in the analogy, it's the whole reason you'd bother.
So the atoms in the egg carton are standing in for the electrons in a real material.
Standing in for them, obeying the same math. And there's a specific piece of math they act out. Physicists call it the Hubbard model, and you don't need the equations, just the tug of war inside it. two things compete. An atom would like to hop to the neighboring dimple, quantum tunneling, spreading out, being a wave. But if two atoms crowd into the same dimple, they repel, and that costs energy. Tunneling wants to spread them out and share them around. Repulsion wants to pin them down, one per pocket. And the beauty is that laser knob sets which one wins.
And I bet the two extremes are two totally different kinds of matter.
They are, and watching it flip between them is the landmark experiment. When tunneling wins, shallow dimples, every atom is spread across the whole grid at once, sharing one big coherent wave. That's a superfluid. It flows without any friction. Now raise the laser power, deepen the dimples, make hopping harder. At some point, repulsion takes over and the atoms lock down. Exactly one per pocket, no sharing, no flow. Frozen in place, not by cooling but by cranking one knob. That's a Mott insulator. And the flip from flowing superfluid to locked-down insulator was seen for real in 2002 by a team including Emanuel Bloch and Theodor Hansch, often called the birth of this whole field. The first time somebody took Feynman's idea, built a working quantum imitation of a solid, and watched it change phase on command.
Now, I've been letting you say simulator this whole time, and I need to stop you because in my head, quantum simulator is sliding straight into quantum computer, and I have a feeling you're about to tell me those are not the same thing.
I am, and thank you, because this is the one confusion I most want to head off. They're not the same thing, and blurring them is the easiest way to get lied to about this field. What we've built is an analog, a special-purpose model of one system. You engineer its rulebook, its Hamiltonian, to match the material you care about, then let nature evolve it and watch. What you cannot do is type in an arbitrary program and run any algorithm you like. It's not a general-purpose machine. The honest analogy is a wind tunnel.
A wind tunnel, like for testing airplane wings.
Exactly, and let me label where it holds and where it stops. A wind tunnel is a stand-in. You can't solve the equations for the air over a real wing, so you build a clean, controllable version and watch what the air does. A quantum simulator is a wind tunnel for quantum matter, a clean atomic version of a material obeying the same math that you simply watch. But here's the limit. A wind tunnel only answers the one aerodynamics question you built it for. It's not a laptop. It doesn't run spreadsheets. Same here. A magnificent model of one kind of physics, not the universal, program-anything quantum computer of the headlines. Those headline machines are real and different, a story for another day. Tonight's machine is a model, an analog, a wind tunnel. Keep those apart and you'll never be fooled.
Model, not computer, wind tunnel, not laptop. Okay, that's locked in. So we can build this clean fake solid and flip it between states. What's the state of the art? How good has the wind tunnel gotten?
Ridiculously good, and in two directions at once, seeing and scaling. Let me take you through both, because the real results here are genuinely thrilling, and I don't have to inflate any of them. Photographing the state, one atom at a time. First, seeing. Around 2009 and 2010, two teams, one at Harvard around Marcus Greiner, one in Germany around Emanuel Bloch, built the quantum gas microscope. It does what it says. It photographs the atoms in the egg carton one lattice site at a time, sharp enough to see individual atoms in individual pockets spaced only about 1/2 millionth of a meter apart, and read off which are filled and which are empty.
Wait, so you look down at the grid and read atom here, empty here, atom here? You're photographing the many-body state directly.
Atom by atom, site by site, with near-perfect reliability. Think what that means. In an ordinary experiment on a real solid, you measure a bulk average, a current, a resistance, and infer what the electrons must be doing. Here you just look and see each one. It's the difference between guessing a crowd's mood from the noise and having a photograph of every single face.
And the other direction was scaling, more atoms, bigger models.
Bigger and more ambitious. Two results to hang on to. In 2017, Greiner's group at Harvard cooled a lattice of the antisocial atoms, fermions this time, standing in for electrons even more faithfully, on a small square grid, about 80 sites, cold enough to arrange into an antiferromagnet, a checkerboard where each atom's magnetic orientation points opposite its neighbors, spanning the whole system. Then the crucial move, they removed some atoms, doped it, opening empty sites, up to around 15%. And that matters enormously because a doped grid of exactly this kind is widely believed to sit at the heart of one of the biggest unsolved problems in physics. Hold that thread.
Doping, poking holes in the checkerboard, the closest anyone's come to some famous hard problem. Holding it. What's the other result?
A different, gorgeous platform, from about 2021 onward, tweezer arrays. Instead of a standing wave, you use tightly focused pinpricks of laser light, optical tweezers, to grab individual atoms and place them one at a time in any pattern you like. Then you briefly excite each into a giant, bloated version of itself, a Rydberg state, the outer electron kicked into a huge orbit, so the atoms reach out and interact strongly across real distances. Two teams published back-to-back that year, one at Harvard and MIT around Mikhail Lukin, an array of 256 atoms, one in France around Antoine Broglie, a couple hundred. Both ran them as programmable models of quantum magnetism. Arrange the atoms, set the interactions, and watch a magnet's worth of quantum behavior play out in a pattern you designed by hand.
256 atoms, placed one by one, like beads. And I imagine they haven't stopped there.
They have not. The platform keeps scaling, past 1,000 atoms and then to several thousand in tens of thousands of tweezer spots. But be careful how you read that. Those largest arrays are mostly shown off as scaling records and as candidates for quantum computing hardware, a different use of the same trick, not as a finished, watch-it-answer model of some open physics question. So the honest sentence is, the platform is now scaling to thousands of atoms fast. Not, we've simulated and solved a hard material. Different claims, and I want to keep them apart.
A distinction I might have blown right past. The atom count went up. That doesn't automatically mean a hard problem got solved.
Exactly right. And that instinct will serve you well for the last part, because now I owe you the honest edge, where all this is genuinely powerful and where it very much has not arrived yet. This is the part most likely to get oversold, so I'll be slow and exact. The honest horizon. Start with the dream that pulls this whole field forward, the thread I told you to hold. There's a class of materials called high-temperature superconductors. They carry electricity with zero resistance, far warmer than anyone expected. Discovered decades ago, and here's the scandal, we still have no agreed-upon explanation for why they work. The suspicion is that the answer lives in exactly that doped grid, the doped Hubbard model, hopping versus repulsion with holes poked in it. Solve it and you might crack high-temperature superconductivity. But you can't. It's exponentially hard, and the best classical methods still disagree about what it does.
And that's where the cold atoms ride in. Build the doped grid for real, out of atoms, and read the answer off it.
That's the dream, and I have to be careful with the tense, because this is exactly where hype lives. The 2017 antiferromagnet and the doping experiments are real, genuine milestones, the closest anyone's ever gotten to building that model in the lab. But, as plainly as I can say it, cold atoms have not solved high-temperature superconductivity. They haven't delivered the decisive answer about what that doped grid does in the hard regime. That is the hope, what the whole field is chasing, not banked. So when you hear cold atoms are going to explain superconductivity, the honest word is might, or the dream is, never have shown.
The dream, not the done. So let me push on the why not yet. You said you can photograph every atom, so what's stopping you from just building it and reading off the answer?
Two honest walls, both deep, not engineering hiccups. The first is readout. Even a perfect quantum simulator only ever lets you sample. Every atom-by-atom photograph hands you one random outcome drawn from the wave function, one snapshot. You never read out the entire wave function. There's no way to download the whole thing. And for a big enough system, the number of possible outcomes is so vast that no amount of sampling covers it. You're always inferring the full quantum truth from a spray of samples. And that's built into how measurement works, not a limit of today's cameras.
So even with the perfect microscope, you're looking through a keyhole, one snapshot at a time, and the room is unimaginably big.
A keyhole is just right. The second wall is subtler, and it's why the field is careful about the word advantage. Suppose your simulator gives an answer no classical computer can reproduce. How do you check it's right? Verifying a large quantum simulation is itself exponentially hard classically, past somewhere around 10 or 20 particles. So the machine tells you something and you genuinely cannot confirm it, because that confirmation is the very impossible calculation you built the machine to avoid. Proving a clean quantum win gets tricky, not because the machine is weak, but because the referee is missing.
Okay, but I've definitely seen the headlines. Quantum machine beats supercomputer. Are you telling me those are wrong?
I'm telling you to read them with real care, because this is the easiest place to mislead you. There's a recent, serious result, around 2025, where a quantum machine reproduced the behavior of a hard, messy magnetic system that leading classical methods struggled to match in any reasonable time. Real and important. But three honest caveats, all load-bearing. First, that landmark was done on a completely different kind of machine, a superconducting device called a quantum annealer, not on the cold atom, egg carton of light simulators we've talked about all night. Different platform entirely. Second, claims like that are actively contested. Classical methods are a moving target. People keep inventing better classical algorithms, and more than once, a quantum-beat classical claim has been caught up with or overturned a year or two later. Third, even at its best, it's a demonstration on a model system, not the solution to a standing, open scientific question people cared about for its own sake.
So the fair sentence is really narrow. Not cold atoms have beaten supercomputers, more like
recent experiments are now probing regimes that genuinely strain the very best classical methods. And whether that advantage is durable, whether it survives the next round of cheerful classical algorithms, is being fought out right now. Exciting, real, unfinished, contested. A maturing tool at a threshold, not a finished oracle with the answers in a drawer.
I like that you fenced it so tightly. The fenced version is still incredibly exciting. It's just exciting about something true. Let me try to say the whole horizon back to you, the way you've modelled all night, the proved and the hoped, in two separate hands.
Please. This is the test. Go.
Proved, banked, medals handed out. Condensates are real. First made in 1995, Nobel in 2001. You get there with laser cooling, then evaporation, both stages. Load one into an egg carton of laser light, and it flips from flowing superfluid to locked-down insulator on command, seen in 2002. You can photograph the atoms one site at a time and place them one by one to simulate quantum magnetism with hundreds, the platform now scaling to thousands. All just true.
All true. Every word. Keep going.
But hoped, not done. Using these clean models to crack high-temperature superconductivity is the dream, not a result. And any quantum beats classical claim is subtle. The readout only samples. Verifying a big simulation is itself brutally hard. And the strongest recent demonstration was on a different kind of machine and is still being argued over. A tool crossing a threshold, not a finished victory.
A flawless account, and holding those two hands apart, this is nailed down, this is still being chased, is the whole discipline of doing physics honestly. And here's what I want you to carry out. Every proved thing on that list was, not long before it happened, considered basically impossible. Einstein predicted it, and it sat untouched for 70 years because nobody thought a gas could be made that cold. Then people not much older than you invented two cooling tricks and did it. The frontier isn't some far country you need to be a genius to visit. It started tonight, in your Stat Mech course and your first quantum course. Temperature is motion. Every atom is a wave that grows as it slows. Identical bosons love to share a state. You knew all three. Put them together with enough patience and cold, and you get a new form of matter you can photograph and aim at the universe's hardest problems.
3 things I already owned, holding hands. Exactly the suspicion I walked in with. It just had one more leg than I'd counted, and together they do something none of them do alone.
That's the shape of a frontier. Familiar pieces, one honest step past where the class stopped, arranged into something that looks like magic until you see the seams. And the open questions are wide open. Whether that clean atomic wind tunnel finally settles what makes those superconductors work. Whether the durable advantage is real or keeps slipping away as classical methods improve. Someone has to close them. It could be someone sitting exactly where you are.
One honest step past the homework. I came in ready to catch you overselling a cold cloud, and I'm leaving able to almost picture the whole machine. The lasers, the egg carton, the one wave. Thank you, genuinely.
You could nearly build it in your head. That's the point, and it's true. Go find one of those first photographs, the sharp spike stabbing up out of the smudge. Thousands of atoms agreeing to be one wave, a hair above the coldest anything has ever been. Then go do your next problem set, knowing the edge of the known world is one careful step off the last page of the chapter.
I will. Until next time, keep the 2 hands apart, keep asking what's proved and what's only hoped, and keep an eye on the frontier. It's closer than they tell you.